Now, if we work out the Hamiltonian matrix, we will find a tridiagonal matrix here, because we are considering only nearest neighbor hoppings. Beyond nearest neighbor, the hopping elements are 0. That is what we are assuming. With tridiagonal matrix, it offers certain advantages. Let's see what kind of advantages we have towards our side with this tridiagonal matrix. A matrix whose non-vanishing elements occur only on the principal diagonal and the next upper and lower ones is called the tridiagonal matrix. And the crystal Hamiltonian that we have here in this context can be represented in terms of localized orbitals as the basis. So, we will have basis elements like Fn. These are our basis elements, which are nothing but our local orbitals phi a x minus Tn. So, if we have this kind of basis elements, then the Hamiltonian operator can be expressed in terms of these basis elements as E naught sum over n, all the diagonal elements of the operator, Fn plus gamma sum over n, the off diagonal parts, Fn plus 1 plus Fn plus 1 Fn. This would be the expression of the Hamiltonian operator in terms of this Fn basis, which are localized orbital basis. Now, one-dimensional tight-binding Hamiltonian with one orbital per site and only nearest neighbor hopping is the simplest example that we can describe using a tridiagonal Hamiltonian. And let's represent this. So, the general form of this tridiagonal Hamiltonian is instead of E naught and gamma, we will write just a generic representation, sum over n a n Fn Fn plus sum over n Bn Fn Fn plus 1 plus Fn plus 1 Fn with appropriate values of the diagonal and off diagonal matrix elements An and Bn. We have the Hamiltonian operator as a Hermitian operator. It must be Hermitian. If H is Hermitian, An must be real, because the diagonal elements have to be real of a Hermitian matrix. The off diagonal elements can be complex in general, but we can absorb the complex part of it in appropriate phase factor associated with the basis elements, and if we do that, we can make Bn also real by absorbing the phase factor into the basis elements itself. Now, let us see how we can invert a tridiagonal matrix. That is actually pretty easy, inversion of a tridiagonal matrix. Inverting the tridiagonal matrix would give us the advantage of being able to calculate various quantities quite easily. So let's consider a tridiagonal matrix of the form M is given as alpha naught, beta 1, 0, 0, so on. We are considering a big matrix of finite size, beta 1, alpha 1, beta 2, 0, so on, 0, beta 2, alpha 2, beta 3, so on, 0, 0, beta 3, alpha 3, continued, like this. We have this kind of a big matrix at hand. For simplicity, we consider the rank of the matrix to be finite but arbitrarily large. If we call the inverse of this matrix to be M inverse, then we are primarily interested in finding the explicit expression of the elements in here. Let's consider the first element, M inverse 0, 0. If we consider how to find this element, then we can indicate the determinant of the matrix M with D naught. This, and then we write D1 is the determinant suppressing the first row and column. Similarly, we can calculate D2, D3 and so on. So, D naught can be expressed as alpha naught D1 minus beta 1 squared D2. So, 1 over M, the 0, 0 element of it is nothing but D1 over D naught. Similarly, with this expression, we can write 1 over M 0, 0 like this equals 1 over D naught over D1 like this equals 1 over alpha naught minus beta 1 squared 1 over D1 over D2. You can see that it becomes an iterative process, and if we iterate like this, we can write an expression of iteration like 1 over M 0, 0 equals 1 over alpha naught minus beta 1 squared over alpha 1 minus beta 2 squared over, it continues like this, minus beta naught squared over alpha minus 1 minus beta minus 1 squared over, it continues like this. So, we have written continued fraction expression for the elements of the inverse matrix. Now, in this case, we have beta naught equals 0. Then we obtain the previous equation that we have discussed earlier. So, this method, using this method, we can obtain any of the diagonal elements of the inverse matrix. Also, there is a formalism to get the off diagonal elements of the inverse matrix, similar formalism. And this using this continued fraction expressions, which doesn't go to infinity because we are considering matrices of finite size, it can be easily evaluated using a computer. There is no problem with this. Now let's consider the density of states. If we consider a system described by a Hamiltonian, the Hamiltonian is H, and let's say it has psi m normalized eigenfunctions, corresponding to Em eigenvalue. Then the total density of states can be defined as dE equals sum over m delta function of E minus Em. Consider this definition, think about it carefully, and you will be able to reconcile its meaning with whatever we understand from our previous notion of density of states. This is consistent with that. So, if we integrate the density of states, then we are going to get the number of states. If we integrate it over the range from E1 to E2, we get the number of states in this energy range. The density of states, if we consider it projected onto any arbitrary state of interest, let's consider F naught to be the arbitrary state of interest. Usually local orbitals happen to be our states of interest, then we can project the density of state onto this orbital. That means we can get the local density of states provided this F naught is a local orbital. So, the density of state projected on any arbitrary state of interest, if we normalize it to unity, we can define it as N naught, a function of energy, equals sum over m, the absolute value of the inner product of F naught and psi m, where psi m is the eigenstate, mth eigenstate, square Dirac delta E minus Em. Provided psi m is normalized, F naught is the base, arbitrary basis element. So this is also arbitrary state of interest. This is also normalized. So this quantity inner product squared would be a fraction less than 1 usually, and this gives us something less than the density of states. That's also a function of energy. So the projected or local density of states gives information uniquely on the spectral region investigated by the orbital F0. That means if we want to find out the contribution at a particular energy of certain orbitals, contribution of that orbital into the density of state, we can perform this projection and see what is the contribution coming from that particular orbital in the density of states at that particular energy. And a spectrum can be plotted varying the energy. That's the idea. And if we integrate over N0 as a function of energy over dE, we will get it equals to 1 just because F0 is normalized. The total density of states is just the sum of the projected density of state over the complete orthonormal basis set. So if we consider the entire orthonormal basis set Fn and project the density of state onto each elements and sum them for a particular energy, then we will get the total density of states.